practice problems from fractions that we just learned in the past classes. We'll go over some questions, and as you can see here that many of the questions that related to fractions can be expressed as a word problem. That is because the concept of fractions can be used in many different places in our daily life. So the first question here, suppose we have a woman begins her work at 10:20 a.m. and we know that it's estimated to be finished with 5 and 9/10 hours. So then what exactly the time that does she expect to finish this job? So we have the starting point, which is 10 o'clock and 20, and we want to know at what time it finishes. And then we also know the length of this work, basically how long does it expect it to finish. So it takes 5 and 9/10 hours to finish. Right, so looks like we need to add up the hours that expected to be spent during work to the starting time, and then the results or the outcome should be the ending time or the time that when she expect to finish. So there's actually two different ways that you can do, because this number is already a mixed number. You can either separate the hour parts or the integer parts to representing the hour, and then the fraction part that to representing the minutes, add them to the original time separately. Or you can convert this number into one single fraction first, and then that single fraction is the not rounded number of hours, or that can be converted to minutes, and then you can add it back. So looks like the first way is easier. So 5 9/10 hours. Another maybe friendly reminder is that when you working on any sort of word problem, because the word problem coming from your daily life, and in our daily life, quantities are having units. For example, when we say 5, we need to say 5 hours. Otherwise, people would ask whether this represents 5 minutes or 5 seconds, so 5 hours. In some other questions, you will have like 10 kilometers or 10 meters or whatever different units. So it is very important to always keep your units after the number. So this equivalent to 5 hours plus 9/10 hours, right? This is just the first step to write this apart with the integer part and the fraction part. Now, for 5 hours, it's already a rounded number. It's already an integer number. I don't need to do anything for now. But then for the fraction part, I can then convert, because this is not 1 hour. This is 9/10 hours. It's not a rounded number. But if you convert this to minutes, let's see what happened. So how to convert hour to minutes? If you don't know, 1 hour is 60 minutes, so that an hour can be written as 60 minutes. That means this hour is equivalent to 1 times a hour. Nine over 10. Now this 1 times an hour can be replaced because of this relationship, because of this equation. This can be replaced by 60 minutes. And then further simplifying this divided by 10 is 6, 6 times 9, 54 minutes. Now I can make a pause here. I already separate this number into all integers or all rounded numbers, and I have 5 hours and I have 54 minutes. So what happens if I start, now I can start adding this to the starting time, right? So 10, 20 plus 5 hour 54 minutes is hour by hour and minute by minute. Now 74 minutes, we never, recording our daily life, we should never see such minutes as 74 minutes because it's exceeding the 60 minutes, and as long as you pass 60 minutes you add 1 hour. So 74 minutes can be further written as 60 plus 14 minutes, then 60 minutes is 1 hour plus 14 minutes, right? So then this can be further written as 60 plus 14 minutes. So this 60 will be rounded. I probably shouldn't write in this way. I just want to demonstrate how extra 60 minutes being rounded or added to the hour. So it should be 15 plus 1, right? Hour plus 1 because it's this. The minutes become 14. So it's 16, 14. So that means this lady would expect her work to finish at 16:14 p.m. Right, so that's how you solve this question. The second one, to compute or to simplify this expression. Before solving this, let's see if we can find the pattern, and it does has a relatively clear pattern such that we are adding like terms by terms, and within each term and there's one or two numbers are keep accumulating plus 1 term by term, and then you can also find that the second term, if I multiply the integer in front of the brackets into the brackets, the second term is always cancelled out and end up with -1. So that means it looks like the easiest way is to multiplying the integer in front of each bracket first. So the first one, 2 times 1 is 2, minus 2 times 1 over 2, which is 1. We'll rewrite it later. The second term, 3 times 1, minus 3 times 1 over 3. And keep going on and until the last term is 10 times 1 minus 10 times 1 over 10. Now start simplifying this. I have 2 minus 1, right? And I can also taking out the brackets. Plus 3 minus 1 plus the next term would be 4 minus 1 plus until the last term is 10 minus 1. So I always has a number 2, 3, 4, 5 until 10, and I always have a minus 1, minus 1, minus 1. How many terms do I have together? Right, I have this, and I have minus 1 plus minus 1. Each minus 1 would have a bracket. So then the question is, how many terms do I have? I have equal numbers of terms in the two square brackets, but how many? Now I have 2 counted to 10. Remember what we learned in the first class in arithmetic. This means I have 10 minus 2 plus 1, which is 9 terms. And same here. So then I don't have to teach you many different options. You can try by yourself, but one way is to have the pattern that the first term sums the last term, and then second term sums the second last term. So I have 12 times 4 such case, plus what is the middle term, the fifth term, which is 6 is the middle term. And then I have also 9 terms over here. Each one of them are -1, so I have -9. So I have 48 plus 6 minus 9, 45. Okay, so this is this question. All right, so next is also a word problem. So Sam purchased 3¼ pounds of cheese. He used half of the purchase made for a casserole, and then ¼ pound of the cheese for sandwich. Now use a mixed number to demonstrate how much cheese he has left. Okay, here this is again a word problem. As I just mentioned earlier, that I strongly recommend you to, when you're solving the word problem, you should keep both the quantities and their units together so that you won't mix it up, because units has their own conversion rules. And if you unfortunately express your numbers under different units, you will for sure get a wrong answer. And this example going a bit even further than that, because it has a mix of, it has information, contains a number and the units, like a ¼ pound. It also contains the information of like half of the purchased cheese. So you can see here, it's not a direct number with units, but it expresses a percentage of the original amount. So let's see how do we do this. But by the end, to solve this, how much has left, we will need to calculate the quantities, how much being used for casserole, how much being used for sandwich, and then what left is what has been left. So that means casserole, let's read this again. He used half of the purchased cheese for casserole. So what has purchased is 3 and 1/4 and ¼ pounds. And then half, which means you multiply 1/2 or divide by 2, is used for casserole. So then simplify this again. My preference would to convert this to a one single fraction first. So it's 13/4, then times 1/2 pounds. And then this gives you 13/8 pounds. Okay, so this is how much being used for casserole. Then sandwiches. So for sandwiches, it's a direct number, so it's 1/4 pounds. Okay, so I have the quantity of how much being used for casserole, how much being used for sandwich. Then what has been left is the total amount, what being purchased, subtract what being spent for casserole, and then subtract what being spent for sandwich. And then it's just do the fraction subtraction. Let's see. Again, I would convert this to a single fraction of 13/4 minus 13/8 minus 1/4. And then remember, for fraction addition or subtraction, I'd want to have this to convert to the same denominator or the common denominator to simplify my calculation. So here, obviously, the common denominator is 8. So the first number becomes 26. The second number doesn't change, 13. This becomes 2, so that they all have common denominator of 8. And then 13 minus 2 is 11/8, and there's no further factor to simplify this number, so that's the simplest form now. And don't forget the unit. So that means there's 11 over 8 pounds left. Or if you want to further write as a mixed number, because 11 is higher than 8, so it's 11, sorry, 8 plus 3 over 8, so it's 1 and 3 over 8 pounds left. So it's 1 pound and 3 over 8 left. Right, so this is how to solve another word problem. Let's see the next. Express a as a single fraction to this expression, basically to simplify them, or by doing the additions and multiplication, and then to get the simplest form. So this one, right, always observing your question before you start writing. You can see in some places you have the common numbers from the numerator and denominator. Seems that you can cancel them out, but it doesn't true for every single term. Like in many other cases, you don't have a common factor. And in fact, I also do observe that they have common multiples in front of each fraction. Not only just this common multiple, but the denominator of 44 seems also in common. So then perhaps the best way is to start from taking out the common factor and then do the addition of the rest terms first. So 7 over 19 is definitely a common factor. And then 44, I'm writing in this form. 44 in the denominator is also a common factor. So then what else left? It's 13 plus 19 plus 25 plus 31. So let's see if we write that summation together, can we go further simplified? So this 19 and 31 is 50, and the 13 25 is 38. So it's 7 over 19. This happened to be 88 over 44. Then clearly 88 is 2 times 44. So it's 2 and times 7 over 19. So it's 14 over 19. And between the number 14 and 19, they're relatively prime. There's no common factors. It's 14 is also less than 19, so there is no further simplifications to this number. So that's your answer in the simplest form. Okay, our next question is to evaluate the following expression in the simplest form. So this one, as you can see, you have 3 fractions in each places with a certain power, and then you would want to then, of course, cancel out the common factors from this large fraction on both denominator and numerator, and then to get your simplest form. So looks like intuitively there's 2 ways. The one way is to take the power first, and then write all the numbers in their correct order, and then start comparing the common factor between the numerator and denominator, and then do the simplification. So this is one way, but seems like it's going to give you many large numbers, like 4's power of 25. It's going to be a pretty big number. So there's one other way, like go other way around. Instead of taking the powers of all such known number, we also know that each number can be broken down into the multiplication of prime numbers. They're prime factors. So basically the prime factorization will convert every single number into a series of the multiplications of prime numbers with certain powers. And then we can compare the powers from each prime number to further simplify this expression. So this sounds either way, so let's try this way. The number 6 over 5. So 6 has prime factor of 2 and 3. So it's 2 3. 5 has no further prime factorization. 25 is 5 times 5, right? So it's 5 squared. And then 36 is 6 squared. 6 is 2 times 3, so it's 2 squared and 3 squared. Okay, so those are just prime factorization. If you are not clear, you can try by yourself by writing down the factor tree, or to write it step by step by yourself. And then the next term, remember the reciprocal of the fraction. If I divide it by 1 over AB is B over A, right? So then this can be kind of flipped to the top to become 6 over 5 with the fourth power, right? And then 6 over 5 with the fourth power is, I'm gonna write one more time. That 6 is 2, 3, 5 is just 5. Okay, so now I have multiplications and powers. So then this will be 2, 3, 3, 3. And I can now, because those are all multiplications of fractions, so which means I can write all the numbers on the top into one numerator and all the number on the bottom into one denominator. 2, 4, 3, 4 over, okay, start over again, 5 is 3, I've got to write the fourth power over here, so I have fourth power here, 8, right, let's do this again, so 5, 3, 2 times 4, 8, 2 times 4 is 8, then 5, 4. Okay, so what I have to now reorder the prime factorization from maybe smaller prime to larger prime, and then write the numbers with the same base into one term. So 2, I have power 3, power 4, so I have 2 to 7. 3, I have power of 3 and power of 4. 5, I have just one term with 5 to power of 8. Similarly, in the bottom, 2, 8, 3, 8. 5 is 3 plus 4, which is 7. Then I can cancel out the common factors by comparing their powers, right? Like 2 to power 7, 2 to power 8 is really 1 over 2, right? Because I have 7 2's here, 8 2's here, so all 7 cancel out, I got 1 left. Similarly, so 2, I have 1 left here. 3, 8 is 1 plus 7, so I have 1 3 here. 5, 8 is 1 plus 7, so I have a 5 here. And that's all left. So then it's 5 over 6, and there's no further common factors in between, and that's the simplest form. Okay, next question. For the following expressions, to simplify them and then use your results to square the results and subtract 2 and see what you can observe from here. So first of all, let me write down those expressions. Let us simplify that first. To see what kind of pattern that we can see from there. So let's start from the first one, the easiest one. This is really just the fractions, the addition of fractions and the reciprocal of fractions. So let's just do that one step by step. So what's over here is 2 is 4 over 2, or the common if the common denominator is 2, the numerator of this number will be 4, so 4 plus 1 is 5. Then the reciprocal of that becomes 1 plus 2 over 5, so that's 7 over 5. Okay, let's not doing the square and subtraction yet. Let's just calculate each expression one by one first. This one is 1 plus 1 over 2 plus 1 over, right? This one we just did that. That's 5 over 2. So that becomes 1 plus 1 over 2 plus 2 over 5. Two is 10 over 5 if you want a common denominator. So 10 over 5 plus 2 over 5 is 12 over 5. The 1 over that. And then that's the reciprocal of 5 over 12. And then 1 plus 5 over 12. 1 is 12 over 12, so it's 17 over 12. Okay, the last one, 1 plus over 2 plus this I have just calculated. You can still just do the calculation one by one, but this I have just calculated here, which is 5 over 12. So just taking a shortcut of what I just calculated. So then this is 1 plus 24 over 12. 24 plus 5 is 29, right? This is 1 plus 12 over 29. So 29 over 29 plus 12, that's 41 over 29. Okay, so I have calculated all three terms, and you can see that each expression compared to the previous one are keep expanding this term. So it looks like it's iteratively approaching something. Now let's check the square the results, and then subtract 2. Okay, so let's see the first. Square the results. The minus 2 equals 49, 25, minus 2, 49, 25, minus 2 is 50 over 25 in terms to get the common denominator for the subtraction. And then 49 minus 50 is minus 1 over 25. So it's just minus 1 over 25. Okay, the next in B, I have 17 over 12. Taking the square, minus 2. I have the square of 17. 289. Square of 12. 144 minus 2 is 2 times the denominator in order to have the common denominator for subtraction. So it's 288 over 144. This minus 288 is 1 over 144. Okay, last one, 41 over 29. Taking the square, minus 2. What's the square of 41? 1681. Square of 29. 841 minus 2. So minus 2 means if I want to have the same denominator, this must be the 2 times of the denominator, a 1682. Then the subtraction is minus 1 over 841. Now, do you see a pattern? Every single results we always have just a single 1 on the numerator, and our denominator is keep increasing, actually increased significantly increasing. So as you can see, when this number goes bigger and bigger, the whole expression will become smaller and smaller, right? For example, 1 over 10 is just 0.1, but 1 over 100 is 0.01. 1 over 10 hundreds is 0.0001, right? Every time you adding more numbers on the denominator, the whole, and keep the numerator as 1 unchanged, your results will always getting smaller and smaller. Eventually, it approaches to 0. So this means this outcome, the square, let me use the symbol x denotes the outcome of this series or this sequence. Then the square of this outcome minus 2. I'm not going to say equal. This will be a very important concept in the future when you start learning calculus. It's not equal, but it approaches to 0. So if this approaches to 0, that means x squared approaches to 2. If I move this, if I plus 2 on both sides, or simply move this 2 over here, right? And then further, I can tell, because 2 is a positive number, and this x in this example are always a positive number, then that further means x approaches to square root 2. So this sequence, if I'm keep writing more and more terms, follow this pattern. This is actually a arithmetic sequence that people used to approaches or to simulate the value of square root 2. Okay, now let's take a look at the last question of today's practice class. Suppose there are two different positive integers. Their reciprocals can sum to 1 over 2, or 1 over 3, or 1 over 4, until a general case of 1 over n. How do I find such two positive integers? I mean, here I'm not saying that the same integer will sum to all of them, but if there exists two positive integers that can sum to 1 over 2, and then there are further two different integers that can sum to 1 over 3, and go on, and then eventually can I find a pattern to looking for a generalized case that two integers reciprocals of the two integers are summed to a number 1 over n. Or maybe let's start from the first number 1 over 2 first. Rewrite this question if I need two positive integers, let's say assume the two integers are a and b. The reciprocal sum to 1 over 2 means the reciprocal of a, reciprocal of b, sum to 1 over 2, right? Because these are the reciprocals of an integer number, so there's always equal to 1 on the numerator, and this is 1. And this, to rewrite a little bit, if the common denominator is a times b, then the numerator is a plus b equal to 1 over 2. So of course it doesn't mean that a times b must be 2 and a plus b must be 1, because obviously for positive integers a and b, they cannot add up to 1, right? They cannot be 0 and 1. because for number 0, it doesn't exist the reciprocal. And here, this 1 over 2 really doesn't mean that the number has to be 1 over 2, because they could be 4 over 8, 10 over 20. They can be numbers that are much larger than 1 or 2, as long as they can be canceled out eventually to 1 over 2. So this only means that a times b should be 2 times of a plus b. So how can we find such number a and b's? Maybe let's try a couple random cases from backward. Like, for example, if this number eventually is 1 over 2, there's no solution, no way, because 0 cannot exist in the denominator. How about 2 over 4? That first means I need to have two numbers multiplied to 4. All the factors of 4 are either 1, 4, 2, 2, and nothing else. There's only two pairs of factors of 4. And then none of them are add up to what? To 2. Right? So these are the only two combinations, but if I choose one of the combination, it satisfies that the denominator a times b is 4, but doesn't satisfy the numerator that a plus b is 2. Right? There's no way they can equal to 2. And then you can keep trying. 3, how about 3 over 6? The factor, I need to know all the pairs of the numbers that can multiply to 6 and to check if their sum is 3. So the pair of factors of 6, 1, 6 for sure, 2, 3, and then 3, 2, 6, 1 are the same. So this also has two pairs, and none of them, right? The sum is 7, the sum is 5, none of them sum to 3. So it also doesn't work. You can try as many as you can, but it looks like it's not working well. Actually, when you try the right next one, 4 over 8, 8 I have 1, 8, 2, 4, 3, 4, 4, 2, 8, 1, and nothing else. So this also not going to work. I think until you try to 8 over 16, you will happen to find the first case that you have 4, 4 as a pair of factor, and 4 plus 4 is 8, and 4 times 4 is 16. This satisfies 8 over 16, but unfortunately the question is asking for two different positive integers. If a is 4 and b is 4, they are the same integer, they're not a different integer, so this also doesn't work. So this way things doesn't work. So let's think about if there's any other way. We can start looking at this case where we nearly succeeded. If let's say there's no such restriction of having different positive integers, then I can solve a and b both equal to 4. Then I will have, right, a is 4, b is 4, then I will have 1 over 4 plus 1 over 4. It is 1 over 2, right? Basically, it's the half of 1 over 2 plus the other half of 1 over 2. So this, even though it doesn't work because they are not different integers, but this gives us a hint that we are going back to this expression. We are actually looking for two fraction numbers that are splitted from 1 over 2, right? This case, it's split half and half, or split it evenly, so that it works, but it doesn't satisfy this different condition. But this hints us that how about we split this non-evenly such that the results will be different, but this would also work. So that means 1 over 2 can be split as different portions, right? Okay, let me just rewrite that in another way. So this means if I split evenly, I need to times 50% here and 50% here. This gives you 1 over 4 and 1 over 4, right? This is another way to express how we get the fourth solution, but it is one of the possible way to get a solution. So now, if I cannot do this half way, can I still find a way? This means in the first component, I still need to multiply it with 1 over something, because the final results is reciprocal of integers. The numerator always 1. So here you cannot multiply something other than the numerator equal to 1, otherwise your outcome numerator won't equal to 1. So it's 1, and looks like I need multiply 1 over something. As I said, not split half in half. I can split into 1/3 versus 2/3, or 1/4 versus 3/4, right? So let's see 1 over something here. Then the next number, it cannot be 1 over here again, because we just tried. If this is also 1, your denominator then must be 2, and we're going back to this case, which doesn't work. So this number, I don't ask this have to be 1, because there's 2 scenarios can make your outcomes, the outcoming fraction also having 1 on the denominator. By how? Either I multiply a 1, or I multiply here, this in this case this is 2. So if I multiply a 2 with something over here, I can still cancel this out and still get my outcoming fraction with numerator of 1. Now, then this seems that I have fixed the choice of the numerator now. I must put 1 over here, then I must put a 2 over here, which means the denominator must be 1 plus 2, 3. Why? Because I'm splitting this number, means the ratio or the percentage used to split must always sum to 1, right? It's like you're splitting a cake, then if you splitting 1/2, the rest must be 1/2. If you're splitting 1/3, the rest must be 2/3, because they always sum to 1. So the actual formula how I get to know the denominator is that they first must have the same denominator, and then they must sum to 1. So that's I have 3 over x equal to 1. X is 3. So that's actually how I get to know, in this case, denominator must be 3. So then this multiplication give you 1 over 6. This gives you, the 2 cancel out, so it's 1 over 3. So that means my A is 6, B is 3. And let's verify. Reciprocal of 1 over 6 plus 1 over 3 is 1 over 6 plus 2 over 6, 3 over 6, which is 1 over 2. Right, so it is 1 over 2. It is reciprocal of integers 3 and 6, and they are different integers, different positive integers. Now you seems to see the pattern. Let's try the next one. How to find 2 such integers that sum up to 1 over 3. Let's use the same way by checking how to split this number. I still want a 1 in the first portion of the fraction. Then the next portion, I must have a 3 on the top to cancel this out, to making sure my later on my outcome still is a fraction with numerator equal to 1. And then what's the denominator? What's the denominator to making these 2 numbers still sum to 1, or still represents 100%? And that gives you x equal to 4 by solving from here. And in fact, you probably also see that the denominator would always be the sum of the 2 numerators, because I only have 2 fractions. They need to sum to 1, which means numerator 1 plus numerator 3 equals 4, and 4 must be the denominator. So this, if it's 1 over 4 times 1 over 3, it's 1 over 12. This one, 3 cancel out, this 1 over 4. So this means the two integers are 12 and 4. Okay, let's verify them. 1 over 12 plus 1 over 4 is 1 plus 3 over 12. Common denominator is 4 over 12. It is 1 over 3. So we verified they do sum to 1 over 3. The answer to this question, the two integers are 12 and 4. So I can keep going for 1 over 4, 1 over 5, 1 over 6, all with the same pattern, and I can guarantee to find the results. So let's summarize the pattern. So that pattern will be used with the 1 over n case. So now, if the number is 1 over n can be any number. We still need to split this 1 over n. From what we derived here, the first portion in terms of fraction has a 1 on the top. I don't know this yet. This one has an n on the top, so this can be cancelled out. I don't know this yet. But then the denominator must be the sum of these two. So then denominator is n plus 1. N plus 1. First, to verify, 1 over n plus 1 plus n over n plus 1 is n plus 1 over n plus 1. It is 1 or 100%. So we are splitting this without anything being left out. So these two are the portions or the weights that we split 1 over n. So then do the calculation. This is 1 over n times n plus 1. This is n cancelled out. This is 1 over n plus 1. So that the two integers are the reciprocal of this reciprocal. A should be n times n plus 1. B should be n plus 1. So for any n, if I want to get this 1 over n, my a and b must be in this combination, and they are positive integers, and they are different integers. And finally, so first of all, if n equals 2, we go to this scenario. So if n is 2 means one number is 3, the other number is 2 times 3, which is 6, right? So by plugging in, you verify your solution again. Also, we can still validate the general case by adding 1 over a and 1 over b, that 1 over n plus 1. 1 over b is 1 over n plus 1. And then the common denominator, I need multiply n over here, so it's 1 plus n plus 1. And then n plus 1 and n plus 1 are the same. So eventually it's 1 over n, right? So it is 1 over n. So that's the general formula or general solution to this question.